Alright, so now we're moving into parallel counters. So a parallel counter works a little bit differently because a parallel counter has no lag between the clock pulse counts, the clock pulses, and the counts, which makes them more responsive. Okay, so what do I mean by that? So if you look here, you will see on the ripple counter, this is the transition of our clock pulse, and this is the transition of our flip-flop. So you'll see that we actually get a little bit of a time lag here if we were to draw the way this reacts. Now, if we want to look here on our next transition, because that's our clock pulse, this is our clock, and then we're using the Q of this to be the clock of this one. We're using the Q of this to be the clock of this one. We're then going to get this little bit of lag right here as well. Now the reason we get this lag is because by the time we input a clock pulse into the flip-flop to the time it processes that and creates an output, there is some amount of time lag in there. It's very, very small, but it does exist. Okay? So we get a little bit here, we get a little bit here, we're then going to get a little bit here. Okay, so each time we do this with another flip-flop, we're adding a little bit of time lag to this. Okay, now what we're going to see is the more this builds up, the more and more this is our total lag we have built up so far. So it starts to become kind of substantial over a number of flip-flops that we use. So if we're using a bigger counter here where we have many flip-flops involved in the counter, like if we have, say, we have a 12-bit counter that we're using as a ripple counter, you have 12 flip-flops involved there. So you have this lag happening 12 times every time you're counting. So the responsiveness between the original clock pulse and that final bit is 12 times whatever that lag is. So that actually starts to build up into something fairly significant. Okay? Now that probably doesn't affect us if we're just our simple circuits, but if you were trying to do some type of high-speed counting operation, this starts to become a problem. Okay? Now a parallel counter operates differently because it actually uses the original clock pulse for everything. So you'll see you get this nice clean line here, and you have zero lag between the original clock pulse and all of the individual flip-flops. Now the way this is accomplished is our circuit looks like this. I'm going to switch back to my highlighter here, and we will demonstrate this one in Tinkercad as well, but I'll show you the main differences here. So we have our 1 Hz clock pulse. So this is going to connect to the clock in every flip-flop. So that goes up to this one as well. This is why we call it parallel, because it's the same circuit, same wire that connects all these flip-flops together in parallel. Okay? So we're clocking them all at the same time. So this is operating them all synchronously. So parallel or synchronous counter. So the ripple counter was an asynchronous counter. This one is a synchronous counter. Now, how do we actually make it count if we're clocking these all at the same time? Well, the way that we do that is we are actually manipulating whether or not each of these is actually in toggle or hold mode each time. So if you remember, if you put J equals 1 and K equals 1, that gives us toggle mode. Okay? So on the very first one, J and K, both tied to 5 volts. So this first one is always in toggle. Clear is always set to 5 volts as well. The way this works on the second one, we are going to say if our output Q on the first one is on, then we are going to enable toggle mode on the second one. Okay? The way we're going to do the next one, we're going to say enable toggle mode on the third one if there is a 1 in both of these. Okay? If we have 1 and a 1, then enable toggle mode here. The way that we do that is we actually need to do a little bit of logic for it. So we're going to actually use an AND gate and say that the result of this AND gate will be as if we have Q from here and Q from here. Okay, so that'll basically mean that we have a 1 and a 1. If that is true, give us toggle mode here when we clock it. And we will just keep on cascading that same concept throughout this. So give us toggle mode here if we have, once again, an AND gate, a 1 from here, and the result of this AND gate indicated that we had 1s both here and here. So if everything to the left is a 1, enable toggle mode here. So to look at that on a table, we are basically saying, my pen going here, let's think of this in red. Let's look at this as 4 bits. So we're going to clock these all. This is always just going to toggle. This first one here, this is always going to toggle back and forth every time we clock it. This first bit here, what we're looking at here is when we clock it, we're going to toggle if this is already a 1. Sorry, if this previous line is a 1. So if that's a 1, we're going to toggle. That's not a 1, so we're not going to toggle. This is a 1, so we're going to toggle. Not a 1, so we're not going to toggle. Is a 1, so we're going to toggle. 0 is a hold, 1 is a toggle, 0 is a hold, 1 is a toggle. Okay? The next one here, we're going to look at this. 0 is a hold, 0 is a hold, 1 is a toggle, 1 is a... So we need to look at, everything here now. Did that one wrong. So we are now looking at both of these. So that's a 0 because we need 1s at both of these. If we have a 1 and a 1, this is basically this here. We do a toggle on the next operation. So now we do a toggle. So we do a toggle again over here. But these will all be, that's a toggle back to a 0. So these will all just hold. Same thing here. We're going to do a toggle at this operation. Everything else is going to be a hold. So hold, 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 hold until we get all 1s. Then we do a toggle. Okay? And we basically just built our binary counting chart there. Okay? So that is the parallel counter. Now how many gates do we need to build this? Little formula for that. It's basically for n number of bits, you require n minus 2 AND gates and n flip-flops. So basically if you have, let's say you wanted to do 6 bits, it would look like this. You would have 6 flip-flops. You basically don't need one for the 2 ends, but you need one. You need a a gate, an AND gate in between each of the intermediate ones. So basically N minus 2, and this is going to produce, so you get all your wiring in between here, very complex wiring. So this is 4 6 flip-flops. Okay, and that will be able to produce a 6-bit number. Okay, so this gets very complicated when you start wiring these, as we will demonstrate in Tinkercad. Okay, so this will be a Tinkercad demonstration of the parallel counter. Okay, this one is the parallel counter. Now this one is a real nightmare to wire. This is probably the most difficult wiring challenge that we have on the physical breadboards. If you're actually trying to wire the boards themselves, this one gave people a lot of trouble last year when we were doing this in the physical lab, from my memory. So the way this one works, you will see here, I've reduced some things out of this to make it simpler. So I got rid of the our multi-vibrator circuit, and we're just running the clock signal off the function generator to make things simpler. So we have a 1 Hertz signal coming in. So that's the orange wire represented here. So now this clock signal goes to the clock on each flip-flop. Okay, so these are all being clocked at the same time off of the same signal. So before, what we had was we would clock the first flip-flop, and then the output of that flip-flop would clock the second one, the output of that one would clock the next one, and so on and so on. They kind of cascade like that. And because you're doing that, you're building a little bit of delay into each transition, because you have to wait for, you get that original clock signal, and then your flip-flop actually has to process that, and you get a slight delay in there each time. Now, you don't notice that at all, but if you're trying to count fairly large numbers with this, that delay does build up with each bit that you add. So if you're trying to have a relatively large number with a lot of bits, that delay just keeps on building, building, building. If you're trying to count fast with a fairly rapid clock signal, by the time the difference between getting that clock signal and your last bit actually registering that it has been clocked, that's a significant delay and affects your processing. So the parallel counter is better because all of your flip-flops are clocked at the same time. So the way that we count with this is we are basically changing whether the flip-flops are in toggle mode or not. So the way that we do that now is we are now controlling whether the J and K inputs are on or off depending on what the state of all the previous flip-flops are. So what we do is we clock them all at the same time. So we look at this first one here. Its J and K inputs are just tied to 1 or tied to 5 volts all the time, so it's always in toggle mode. The second one is dependent upon if the output of flip-flop 1 is on or not. So you'll see the output of flip-flop 1 is right here. So that does a couple different things, but it also connects to K2 and J2. So if output of flip-flop 1 is on, that will put flip-flop 2 in toggle mode. So when we clock it, flip-flop 2 will actually toggle. The way that we handle the third one, we are going to determine J1 and K1 on the third one. That is going to be an AND function, which is basically the result of this purple and yellow wire here, which are output 2 and output 1. So if flip-flop 1 is a 1 and flip-flop 2 is a 1, that will produce a 1 as our result here. So if we have a 1 and a 1 in our first and second bits, at the time when we clock it, then we will put the third bit in toggle mode. So basically we have a 1 and a 1, which is a representative of a 3. Then when we clock it again, we will toggle that third bit, which takes us to a 4, essentially. And then we keep on cascading like that. So we're basically using AND gates to look at, are all of the previous bits at a 1 state? If they are, when we clock the next one, we will toggle that bit as well. But we need to have every other bit previous to it as a 1 before we can set the next bit. And that is how the parallel flip-flop, the parallel counter works. You can see it in the truth table. Okay, so slightly faster, but not noticeable to the human counting ability with the parallel counter. All right, back into it here. I'm going to do a couple other counters, and then we're done for this lesson. The 192, we do not have this one for Tinkercad, but this is a integrated circuit that has a count up and count down all in one chip. So we're not going to do this part of the lab, but if we did, you would hook up your clock to either the up or the down input, and what you would get is you would get 4 lines of output, so you can create a binary count just by connecting a clock signal to either the count up or count down inputs on here on this chip. So that is the 192 TTL IC BCD up down counter. So we're not going to do that one. What we are going to do is using an equivalent to the lab in the book, or calling out the 74HC393 counter. This is one that's called out in the next part of the lab. We don't have this one, but we do have the 74HC93, which is very similar. So we will modify our lab slightly to use this chip. So you will see here that we do have a clock pulse 1, a clock pulse 0. We've got 2 individual resets here, power, ground, and then 4 outputs to do a 4-digit binary number. The 393 actually does 2 counters off of 1 chip. Our chip only does 1 counter, so we're actually going to use 2 separate chips for our lab. And you can see in the description of this here, which I took off the internet, this is made by Texas Instruments. If you start reading about this, you actually see things that actually start to make sense now to you. So let's read a little bit about here. This 4-bit binary ripple counter. So we know what a ripple counter is now. 4-bit binary ripple counter consists of 4 master-slave flip-flops internally. So just like we would think, this counter has 4 flip-flops internally to it. So it is connected up just like that circuit we did in part A. So a 4 flip-flop ripple counter to create 4 bits of count. Each section has a separate clock input. Do this. And a gated and asynchronous master reset. So we can reset the flip-flops as well. So we can reset everything here. We're actually going to do that in this lab as well. The one thing that is to note here, when I first tried doing this lab, I couldn't get this to work properly, and I wasn't sure why. I actually had to go read this to see what was wrong here. So you can run this in either 3-bit or 4-bit mode. So if we want to run it in 4-bit mode, Q0 must be connected externally to input CP1. So we actually need to connect 2 of the pins together to make this work properly. So I wasn't doing that the first time that I tried this, so I couldn't get it to work. So I had to come back here and actually read this and see that's why it wasn't working properly. Okay? So we are actually going to do this lab here, which is pretty neat. What this is going to do, we're going to do two separate counters, and we are going to count from 0 to 59 with a 1 hertz or 1 second clock pulse. So we are basically going to make a 60-second counter. Okay? So what's going to happen here, we're going to have one set of LEDs. They're going to count our least significant digit, 0 through 9. Another set of LEDs that are going to count our most significant digit, our 0 through 5. Okay? So we're going to have basically our 10s counted over here, our 1s counted over here, and what we should see is this is going to count 0 through 9. Once this hits 9, it will try to go to 10. Now once it does hit 10, what we're going to see is the combination that would create 10, if you think about it in binary. Where is my 10? I'm going to grab my highlighter here. What gives us a 10? So a 10 would be this bit and this bit on. So if we ever got those two bits on together, we would be 10 or more. So we are going to take this and this. We're going to run both of those signals through an AND gate, and we are going to use the output of that AND gate to trigger a reset of this counter. Okay? The other thing that's going to do, so we're going to count up to 9. Once we hit 10, we will actually reset this counter automatically. That'll bring this back to 0, and it'll go 0 through 9 again. So this is just going to continuously loop 0 through 9. The other thing that will happen, when we get this output that says that we've hit 10, this is the signal we are actually going to use as our clock pulse for this one. So every time we hit 10 over here, we will actually increment this counter once by giving it the clock pulse. Okay? Now, we want to make this one reset once we hit 6. So 6 looks like, I'm actually going to do this in a different color. I'll mix up my, so 6 looks like this. This bit and this bit would indicate 6, the 2 and the 4. So once we get these lines here going to our AND, the two of those together will produce a signal here through this AND gate, and this is going to reset this one back to 0. So this will basically loop through 0 through 5. Once it hits 6, it will reset itself back to 0, and this only gets incremented every 10th count over here, and this one gets incremented every 1 second based on the 1 second clock pulse from here. Okay, so we will demonstrate this one in Tinkercad. It is pretty interesting, so that is a good lab there. Okay, this is part E of the lab. So this one we are going to use the 74HC93 chip in the lab, or in the physical breadboard. You have the HC393 chip. Now that operates a bit differently, so I put in the specs for both of these chips in the PowerPoint. So we have the 93 available to us in Tinkercad, but basically this is a 4-bit counter chip. So you can see here I've simplified things quite a bit. So I've just got power supply and function generator. So the orange wires coming in here, that is our 1 hertz clock. So see, I just have an LED, so you can tell when that clock signal is on. And then we basically have 4 output lines from the counter that indicate the 4 bits, and you can see this is basically just counting like we were doing with the ripple counters. And you can see on the spec sheet for this chip there is actually it says that there is 4 flip-flops in here doing a 4-bit ripple count up. So a couple things to note here. I've wired this a little bit differently just to simplify things. So just going straight across with these wires and then connecting them down to make things simple. The one thing I did wrong the first time I tried wiring this, I didn't realize it, and then I read about it in the instructions. For the chip itself, you have to connect output bit 0 to clock 1 if you want to use it as a 4-bit counter. So this wire that crosses over here, you must connect that. If you don't, it doesn't work properly. Okay, so I did that wrong the first time I wired this. Couldn't figure out what was wrong. I actually had to do some reading to figure out what was the problem. The other thing we have here, this is reset 1 and 2 are both tied together and tied to the ground. If you want to count, you do that. If you put a 1 on either one of these inputs, you will reset this back to 0. And we are actually going to do that in the next little chunk of the lab here in part E, where it actually shows us how to make a 60-second or a count to 60 counter using 2 of these chips. So we're going to do that now. So we're basically going to duplicate this and then do a little bit of logic that's going to do some resetting for us as well. So let's duplicate this setup here right now. So I got lots of space on my board here. So let's set up our LEDs first. I'm going to put this down. Where am I going to do this? Let's try it right here. Yeah, we'll go right here. And just for fun, let's make these greens. So basically these are going to be our 1s counters over here. And then we're going to have the 10s over here. So we're basically going to count in 1s, and then every time we hit 9, we're going to add another to our 10s count. And we're going to reset the 1s count. So you can see how it goes to 15 now. So we actually want it to stop when it hits 10. Add another one over here, and reset over here, and then keep on counting 0 through 9 here, and then increment up to 0 through 5 over here. Once we were to hit 6 or 60, we'll reset ourselves back to 0. Okay, so we're going to add another one of these. Put that right here. We're going to duplicate this wiring. So let's bring our clock signal over here. Make that orange. Make that our ground. Power is here. And then we want to go, how do we do this? So 1s. So hit 3, that one goes to here. Trying to lay this out the same way. Hit 0, goes all the way across there. It's going to match the color code with this as well. Just keep it signed and consistent. Oh, it's supposed to go over here. That looks right. That's my yellows. Just try to match the color code so that it's easier to follow. Once I get this done, I'm just going to test this. The black wire. Alright, so these should both now just count up to 15s if everything is good. Oh, I got a crossover here. This one goes to here. That's my turquoise wire. And then do the disable the resets for now. So I should have two sets of counters that just go to 15 at this point. Let's run this. Just make sure this section of it is correct before we add more complication to it. So that looks like it's good. I do like how the green LEDs tend to light up better than the red ones. You can see them a little bit better. Okay, so that looks like it's counting correctly. Alright, so now let's add in the resets. So we're going to do this by adding a little bit of logic in here. So we're going to add in our an AND gate. So we're basically going to say to this first one over here, we're going to say reset if you hit 10. So what bits give a value of 10? So let's think about that. So a 10 would be this LED is on and this LED is on. Right? So if our yellow wire and our brown wire are both on, then we want to actually perform this reset action. So here's what we're going to do. We're going to take this, we're going to tie this to an output on here. You've got to remember as well that I need to actually run this chip. So if we want to run the chip, we need to put ground, power, and then my inputs are going to be brown and yellow. So that's the fourth bit and the second bit. So now if I get that bit combination, both those bits are on together, I have a 10. And if that happens, I want to trigger a reset of this chip. Let's make this one gray. Make that gray. I do like that we have so many colors in here. Things organized. The one advantage we have in here versus the wires you get in the lab. So now what that should do, this one's still just going to count up to 15. This one should only count to 10 and then reset itself. Or should count 0 to 9, sorry. You'll never actually see 10. It'll go 0 to 9 and then back to 0. So let's watch this go. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and now it should trigger itself and reset itself and go back to 0. Okay, so we got that one working. So now we need to do the same thing on this one over here. We want it to reset on 6. Got a black wire, this one a red wire. So what is a 6 over here? It would be this one and this one. So this is our input here. So we have input here. Our output here. I just know that these all happen in threes. I don't even need to look at these things. This wire. Oops. So now we're going to connect. Bring that down here so you can see it better. I like to make my wires all nice and lined up. Let's make this one a yellow so it's consistent. This one's going to be a purple. And we'll make this guy, I actually haven't used green yet, so we'll make that a green. Alright, so what should this do now? So we should see us count 0 to 9 over here, and 0 to 5 over here. We have a 1 hertz signal, so 1 pulse per second. So we should essentially now have a 60-second counter. So let's see what this does. We did that wrong. Okay, so we don't want to okay, so we don't want to clock this every pulse. Move this clock signal over here. The second one we're going to clock every 1 second. This one here, we're only going to clock this when we actually fire this reset. So once we hit 10, when we hit 10, we'll actually clock this. That's how this should work. Alright, so our reset is correct. We're going to reset when we hit 6. But we only clock this and increment our count every time we actually fill up to 10 over here. That is what we should be doing. So we're going to do a reset here. At the same time, we're going to increment over here. Now let's try this again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we got a 1 over here now. 5, 6, 7, 8, 9, 20. 25, 26, 27, 28, 29, 30. 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Coming up to 50. Now once this hits next, this is going to go back to 0. So 58, 59, 60, back to 0. Okay, so that is this running. So this is part E of the lab. So we are counting from 0 through 59 using 2 different 4-bit counters and a little bit of logic in between them. Okay? And that is it for this lab on counters. That is it for this week. We will see you on Thursday.